Okay, so next we go to another slide. So next we start the discussion of Dirichlet problem. Okay, so the kind of discussions what we have done just now about maximum principle, that is very much relevant to define this Dirichlet problem. Okay, what is the consequence of maximum principle? That if D is bounded and connected and U is harmonic function on D and continuous on D closure, then U attains maximum over D closure, okay, on only the periphery, only on the boundary, okay, because the maximum cannot be inside if U is non-trivial. Okay, so this implies that if U and V, two different harmonic functions on D, okay, so they are harmonic function on D, and also they can be extended continuously on the boundary, so they are continuous on the D closure, and they agree upon, okay, they both coincide on the boundary. Imagine, okay, so they coincide. Then this maximum principle dictates that U should coincide with V on the domain itself. Why is it so? Because if U is harmonic, V is harmonic, then their difference is also harmonic, because the differential operator is linear, correct? And then U minus V would be 0 on the boundary, because both are agreeing on the boundary. And then we are having one example of a harmonic function which is 0 on the boundary. So inside, what should be its value? Its value cannot be non-zero, correct? Because then no maximum would be achieved inside the domain. Okay, so then U is equal to V on D. Okay, now we would define what is Dirichlet problem. So Dirichlet problem is actually harmonic functions. The Laplacian U is equal to 0 on the domain D, and on the boundary it is actually satisfying a prescribed function. Okay, a function which is already given to us. Okay, so Dirichlet problem needs specification of the domain D, the boundary data F. Okay, so given D and F, this pair where D is an open domain of Rd and F is a function defined on the boundary of D, real value function, which is also taken as continuous here. Okay, so the problem is to find out function U which satisfies this, or in other words, which is harmonic and which is extendable to the boundary. Okay, so which is continuous extendable to the boundary, so continuous on the closure of D, such that its restriction on the boundary coincides with F. Okay, so that is the Dirichlet problem. Okay, and we know that from the above result that if solution exists is unique, correct? Because if both coincides, okay, so because if you satisfy F on boundary and it has two different solutions, so both coincide on the boundary, so therefore they should be the same in the whole domain also. Okay, so here the result what we are going to show in successive slides. So stochastic representation of the solution of this problem is actually given by a conditional expectation. U of x is equal to conditional expectation of F of W tau D given W0 is equal to x. What is F here? F is the boundary data. Capital W is Brownian motion or Wiener process. Tau D is the stopping time of Brownian motion touching the boundary of the domain, or in other words, it is the heating time of the boundary of the domain. And this formula depends on F and given, and also D, and given any small x value inside the domain, okay, we can find out this expectation. Okay, this expectation need not be finite always. If we have bounded domain, okay, so then this boundary is a compact set, and continuous function on compact set is bounded function. Then we are talking about taking expectation of a bounded function, that would be always finite, there is no problem. But when we say that we are considering any connected open domain, that open domain need not be bounded, right? Need not be bounded. So in that case, we cannot assure that this expectation will be finite. We cannot say that. Okay. So we can only write down this way, provided that expectation of modulus of f of w tau d is finite. Okay. So then we are writing down. Okay. The justification would be given later. So now we just quote the result that this is our aim. Okay. Our aim is to show that. Okay. This is the thing. Now we start this way. Consider this conditional expectation and assume that this is finite. So assume that our domain is such that, I mean, a special case already is there, as we have mentioned just now, that considered a bounded domain. However, just consider some general open domain, open connected domain, such that the conditional expectation of f of w tau d given w0 is equal to x is finite. Then we can define u of x in this fashion. Okay, we are going to show that this is harmonic. So instead of showing the solution of the PD has this representation, we are doing other way. Okay, we are actually considering a special case where this makes sense, and then we are going to show that okay, this function solves the PD. Okay. So in that we have two things, correct? One is that Laplacian of u is equal to 0, another is the bounded data. So for bounded data is concerned, this u defined in this fashion clearly satisfies the boundary data. Why is it so? Imagine that our x is on the boundary. The time 0 Brownian motion is on the boundary. So what should be the hitting time to the boundary? 0. So it is already there. So tau d is exactly 0. So this conditional expectation is that we are going to read this in the following way. Expectation of f of w0 given w0 is equal to x. W0 is no more random because w0 is equal to x is given. So nothing random here. So expectation of this deterministic thing would be just f of w0, but w0 is x, right? F of x. So u of x is equal to f of x on the boundary. So here u satisfies the boundary data is immediate. Okay. So for all x in boundary, u is equal to f is immediate. Now we are considering only the case where x is inside the domain, is an interior point of the domain, and we would like to show that this u, which is defined in this following manner, is actually a harmonic function. But instead of showing that it is harmonic, we are going to show that it satisfies mean value property. Okay, because we have already established that the mean value property implies harmonicity. Okay, so u of x is equal to conditional expectation of no, actually we have not shown that harmonicity in the earlier slides. We have shown that harmonicity implies mean value property, but mean value property implies harmonicity we have not proved. We have just quoted the result and gave the page reference number because that is a little longer proof, so we have not demonstrated here. Okay, so here for all x in the domain D, let R be positive, be such that x, since x is the interior point, that a ball around x of radius r is inside the closure of the domain D. Then from the definition, we just write down EU of x is equal to expectation of f of w tau d given w0 is equal to x, and then we are using tau property of expectation. What we do, we actually put another condition. So this is a sigma algebra which is finer than the sigma algebra at 0. Okay, so it is at the time latter time. So this time is stopping time. The first time the Brownian motion touches the boundary of this ball, what we have written here, that it starts time 0, it starts at x, but the first time when it leaves the ball of radius r around x, that is tau x plus br. So this is stopping time. Okay, so here filtration at stopping time. So this is sigma algebra. So that we condition in between. Conditional expectation of f of w tau d given f stopping time given w0 is equal to x. Now we use strong Markovity of Brownian motion. what is strong Markovity? That conditional distribution of future given past and present, where present is a stopping time, is same as conditional distribution of future given just present. Okay, so here this filtration is actually signal generated by 0 to this time, but that we are replacing by just the present one. The present one is w, the Brownian motion, at tau x, I mean at the time of the stopping time tau. Okay, so now here, so this conditional expectation we look into it. Okay, so expectation of f of tau d given w tau x plus b. Okay, so here we would imagine that, okay, that this point wherever it is at this stopping time, and then it proceeds further, because still it is inside the domain, it would require some more time to leave the domain D. And if you start counting time from there and consider that as 0 time, then this conditional expectation is exactly u of this, correct? Because expectation of f of tau d given w0 is equal to x. Here we have this point, this is a random point, but given that is the random point, you consider that as your present, and that is 0 time, and then you consider, and this is again still tau d, because that would be time to touch the boundary. So that is same as u of w tau x plus br. Okay, as you know, you get ux here, that at w0 whatever the location of the Brownian motion was, that you get u of x as the result of this conditional expectation. So we also get here that w tau x br is, u is evaluated at w tau x br. Now this conditional expectation of u of tau x plus br given w0 is equal to x can be evaluated using integration, I mean using the distribution of Brownian motion. Okay, so here we consider that mu r is, that already in the last lecture we have seen that mu r is the distribution of the Brownian motion on the boundary of the ball of radius r. So here x is the center, and then u of x plus z, where z is on the boundary, and on the boundary we are having mu r is the density of the Brownian motion, and we are integrating with respect to on the boundary set. Okay, u of w tau x br, because this point is always on the boundary of br. So this conditional expectation is exactly this. So this condition x is coming here, correct? Okay, so what is the conclusion? From here we can see that, okay, it satisfies the mean value property. Doesn't matter what my x is, if it is inside the domain D, I can always write down that ux as average of u on the surface of a ball. Okay, x plus b. So using mu r, so hence u has mean value property, therefore u is harmonic on the open domain D, and hence u is also C infinity D. Okay, so this is additional remark, this is beyond the promise what we have made in the statement. So this is one remark which is important. Say we have opted that u is C infinity in D, correct? But this does not necessarily say that u is continuously extendable to D closure. Okay, we have although shown that u is equal to f, okay, on the boundary, okay, and f is continuous, and u is C infinity in D. But that does not necessarily say that if you take a point x n inside of the domain and you approach x n to the boundary, then u of x n would converge to f of x. Okay, so that is not inside the claim, that we are not claiming. It is very important to understand that we are not claiming that. So this no way proves that u is continuous on D closure. Okay, it just says that, okay, on boundary it agrees with f, and in the domain it is satisfying this. Okay, so let us look at the problem again. So here, so find u is in harmonic function and this thing, okay, continuous on D closure. okay, and then we would say that that is the solution, correct? That is the notion of this Dirichlet problem. Okay, but here what we have done is that when this is finite, then you have shown that U satisfies boundary boundary condition, and also harmonic. Okay, but that does not say that. Okay, so we have not proved that U actually solves this Dirichlet problem. We have shown that these two things separately. I mean this line we have proved, this line we have proved, this fact we have proved, but this is not done. Okay, this needs additional condition on the geometry of the boundary. Okay, so that is required. So this needs some sufficiently regular. We are going to see more detail. I mean, it would take some time to go into the deeper discussion about that. Okay, if f is bounded, okay, so now let us go to even smaller subcase classes, okay, some special cases. If f is bounded and the stopping time, okay, or hitting time to the boundary is finite with probability 1 for all a in D. Okay, so this is clearly the case when domain is bounded. If domain is bounded, boundary function starts here, and of course it touches after some time. I mean, it never touches and stays there forever, the probability is 0. So probability that tau d is finite, that means at a finite time it touches, that is probability 1, right? The probability is 1. Okay, so this is true for a very special case where D is bounded, but we are not assuming D is bounded here. We are just saying that okay, let us assume our D is such that this is true. So perhaps some other unbounded domain also may satisfy this condition, correct? So we are allowing that scope, and also we are assuming f is bounded. I mean, that is the reason we need to assume this. I mean, if D is already bounded domain, we did not need to assume f is bounded. Okay, but since we are not putting that restriction, so we are allowing us to be a little more general. Okay, we are just assuming this condition and f is bounded. Okay, then any bounded solution of df, okay, is indeed this conditional expectation. There is a typo. I mean, this bracket would appear here. Okay, conditional expectation of f of w tau d given w0 is equal to x. Okay, so this is a positive result. This is a complete result. Okay, so earlier was the intuition behind that why should one expect such kind of representation, but under this special condition one can actually get it. Okay, so we are going to see the proof of that. So let U be a bounded solution of the domain D comma f. Okay, why do we talk about bounded solution here? The main reason is that f is taken to be bounded, and we are looking for solution of Dirichlet problem. Right? So U is harmonic. So harmonic function has maximum principle. So maximum value whatever it can take would be f, correct? And f is bounded, so U is bounded. Okay, okay, so let U be a bounded solution to df. Okay, that does not mean that df would have. I mean, so here we are just taking that. Okay, if so, df has a bounded solution. Now we consider dn. Dn is, these are like annulus kind of things. What are these? We are fixing 1 over n, a small number. Okay, and considering x, I mean the norm, because this is d-dimensional space, correct? So x minus y norm. So the distance, the d-metric distance of x and y is greater than 1 over n. Okay, so we are going to get a strip. Okay, I mean the complement of a strip, correct? Where so all possible x y, but then if I choose y to be on the boundary of the domain, okay, then given x, I am looking at all possible y, okay, on the boundary domain, okay, and looking at only those x such that the minimum distance is more than 1 over n. So that means that if you have a boundary and if you have an annulus of annulus means here, like, it would not be a circular annulus but a annulus sphere or some hollow sphere kind of thing of thickness 1 over n, and x is below, outside of that, x is even inside that. Okay, x is inside the domain, and also it is not it is little away from boundary, it is 1 over n distance away from boundary. Okay, so that is my dn. So dn is actually a subset of D which is away from boundary of D. So the question is dn open set? Yes, dn is open because this I have greater than, strictly greater than sign on over. Okay, but dn could be actually empty set also, because if D is very small, its radius itself is less than 1 over n, it will be empty set. But okay, dn is an open set. Now we use Ito's rule. For that we take time as the minimum of 3 different stopping times. Okay, so here, I mean, this is t actually, this not be tau. I mean, t is a time, and another and t tau bn and tau dn. Okay, here let us see the proof. Okay, for proof we consider bounded solution. So even if the boundary data is bounded, when domain is unbounded, we cannot assure that the solution would be bounded also. There could be many unbounded solutions. We are going to see a very specific example after completing this proof. So here we consider the bounded solution only. Okay, so let U be a bounded solution to the Dirichlet problem df. Define dn. Dn is the set of points in X such that which are 1 over n distance away from the boundary. Okay, so infimum of over all possible y in boundary. Okay, and then x minus y. So it is like, let me see if I can draw something here. If domain, if this is D, and then this is del D, and then if this much distance is 1 over n, so this part would be dn. I mean, this whole thing is D, but this is D. Okay, fine. So now what we do is that we consider U value, the function U, evaluated at the position of the Brownian motion at time t minimum. This is typo, this should be t minimum, the stopping time of ball of radius n and hitting time of the boundary dn. Okay, so where did we start from? We start from it w0 at time 0, and then we look at the time t. Okay, if the Brownian motion position, Brownian motion does not leave the ball of radius n, neither it leaves the domain dn, and if it leaves, then we just take minimum of these, whatever, say either ball of radius n or ball of or the dn. Okay, so let me clarify that dn here is an open set because we have strict inequality here. Okay, it could be an empty set, but if it's non-empty, it will also be an open set. Okay, so now we use Ito's rule. So Ito's rule would imply that U of W of T minimum tau B n minimum tau D n is equal to U of W0 plus integration of del U del X dW I. So it is multidimensional Ito's formula. Here along all components we need to integrate I is equal to 1 to D. Also it has Ito's formula gives another term, second order term, that second order derivative del 2u del xi etc. And but there in that term we are going to get dwi dwj, so cross covariations. Okay, cross covariation of w and then second order derivative of u. Now there what we are going to observe is that that term would not appear here. Why? Because when I and j are different, since a d-dimensional Steiner-Brownian motion has all components independent, so cross covariation of dwi and w and wj would be 0 when I is not equals to j. So here, out of these n square terms, n square minus n number of terms would disappear, and then the terms where I and j are equal, those would remain. However, that would also not contribute here for one single reason, that because there we are going to get the summation, because dw, I mean the quadratic covariation of wi with respect to wi, okay, w quadratic variation we call that, is just s, okay, for every I it is the same s. So the summation would be only on this term which would remain there. So let me try to write down this. The term what we have not written is del 2 del xi del xj u of ws d wi wj s. This term we have not written. I mean, the reason is that in this term, as we have already sum over all possible I and j, as we have already mentioned that this sum can be written in two parts, I not equals to j part I not equals to j part, and in this part this quadratic covariation becomes 0 because these w and wj are independent. So, this part becomes 0, and another part is I is equal to j part. So, I is equal to 1 to d dimensional things, del 2 del x I square, because I is equal to j now, yeah, u w s, and then d wi wi s, okay. So, that is like quadratic variation, so ds. However, this part is Laplacian of u, but u is harmonic, so this is also 0. So, this whole term, okay, becomes 0 here. So, that is the reason that, so we do not get the second order term here. Ito's rule implies, okay, and also that u is harmonic together implies that u of w t minimum, so here it is t minimum tau bn tau dn. And what is tau bn here? I mean, so if you look into this thing, say you have started from here, so that is that you imagine that is your w0, and then you take ball of radius say 1, and then ball of radius say 2, so this would be b2, etc. Consider, okay, consider taking various different ball of radius, this thing. Why are you doing so? Because d itself is need not be bounded, so therefore dn also need not be bounded. However, this bn should be bounded for each and every n. So here this tau bn minimum tau dn, which is same as tau of bn intersection dn, okay. So this becomes bounded domain, okay. So as bn is bounded, on that bounded domain, the continuous function del u del x, u is del u del x continuous function, correct. So that is continuous function on a bounded domain is also bounded, correct, because it is continuous function on the whole domain, and if you take a bounded domain there, and the closure is also bounded, so closure is closed and bounded set on a compact set. So on a compact set the function is bounded. So del u del x is also bounded on bn, so this is n, okay, there is a typo. So here on the right hand side, here whenever s is running between 0 to this time w never leaves the domain dn and bn, and therefore the value of del u del x which are explored are always less than or equals to the maximum value of del u del x on bn. So this part remains bounded. Since this integrand is bounded, so it is square integrable class, and then this stochastic integration of this bounded integrand with this Brownian motion is a martingale. Therefore, its expectation is 0, and finite sum of expectation, that would also be 0. So, expectation of u, I mean this left hand side is nothing but expectation of u w 0, but w 0 is certain. So, it is u w 0. So, w 0 is the starting point of Brownian motion, which we take as a, the point a, okay, and a is in the domain Dn, as we have seen in the picture. So, this is our a, okay, it is in the point Dn. So, here u of a is expectation of u of w t minimum tau bn minimum tau dn. Yes, now here it is correct. Yes. So, this is t, okay. So, this t is appearing here given w 0 is equal to a. So, this is true for all possible t non-negative and all possible n is equal to 1, 2, 3 etc., and also for all possible a in Dn. Okay. This is a vertical line here. So, since probability that heating time of the boundary finite is 1, because that is the underlying assumption, okay, we started with this. So, since this is the fact, so that means starting from a, okay, in a finite time it would surely touch dn, okay, I mean this tau dn, okay. So, now as we are letting n tends to infinity, what would happen? That when n is very large, okay, so then this time to leave the ball Bn, okay, would increase, correct. So, tau Bn goes to infinity, tau Bn, because tau Bn is the stopping the heating time of the boundary of ball radius n, okay. So, as n tends to infinity, this tau Bn becomes larger and larger, okay, and also you allow n tends to infinity. So, t also becomes larger and larger. So, this thing. So, if you now consider the minimum of these three things, then tau dn becomes the minimum, okay. So, as n tends to infinity, okay, this becomes large, and then this random variable converges to u w tau d, okay, almost surely. The p superscript is saying that, okay, the conditional with the conditional probability that we start at point A, okay. So, this is not 3, this is b actually, bn, yes, almost surely as n tends to infinity, t tends to infinity, okay. So, now we would use dominated convergence theorem. Why? Because here u is bounded because here we have started with a bounded solution, okay. Since we have started bounded solution, so we would take the advantage of that. So, we have now here a sequence of random variables, bounded random variables, since u is bounded, which converges almost surely. Now, our goal is that expectation of this, okay, sequence of expectation, that will also converge to the expectation of right hand side, okay, expectation of right hand side. So, u of a is equal to limit n tends to infinity, that I can write. Why? Because this is true for all possible n. So, I can take limit n tends to infinity here. So, we are doing precisely the limit n tends to infinity u of w t, again t here, t minimum tau dn minimum tau bn, okay, not both dn, bn minimum dn, given w 0 is equal to a. So, that is expectation of u w tau d. Using this part here we are using dominated convergence theorem DCT, that we can take limit inside, okay, w 0 is equal to a. However, what is the value of u at the position w tau d? So, tau d is the time when the Brownian motion touches the boundary of d, but when that means this is the locus of the boundary. At that location, u is satisfying the boundary condition, the boundary data is f. So, u of w tau d is f. Why? Because u satisfies the Dirichlet problem, the bounded solution of the Dirichlet problem. This is expectation f w tau d. So, what did we prove? We have proved that if u is a bounded solution of the Dirichlet problem d comma f, where d is such that stopping time or heating time is finite almost surely, and f is bounded, okay, f is bounded, then that solution of the Dirichlet problem has this representation, can be written this way: expectation of f of w tau d given w0 is equal to a. Okay, the problem has this solution.